All right. Thanks everyone for showing up so early. Today I have the great pleasure of welcoming a good friend and collaborator, David Romero. David did his PhD at the VU, still actually finishing his PhD at the VU. But in the meantime, he's already started work at NVIDIA, where he, amongst other topics, works on long context architecture, which is something he's going to be talking to us about today. So, without further ado,
thank you. Yeah, thank you all for coming. Can you hear me all right? Yeah, perfect. Right, so yeah, we're going to be talking about architectures other than transformers. The idea here is that we're going to explore some alternatives to transformers that give us some properties in terms of scaling that I think are very, very interesting, and I think are going to be more and more relevant in the future when we try to scale things up, basically, more and more. So this is a little bit what we're going to talk about today. We're going to start with state space models, basically because they give an interesting framework to start formalizing everything. And then we're going to talk about two different classes of models, which are called here generalized convolutional models, and then generalized recurrent models. From these types of models, the most known ones are Hyena, this one here. Can you see my mouse, by the way? Oh, yeah. Online, can you also see my mouse? Yeah, OK. And of course, Mamba, which has been very popular in the last few months. Funnily, the paper didn't get accepted at iClear, which is shows how much of a random process it is. But it's always interesting to see. Cool. First of all, some acknowledgements. So a lot of the material that I'm going to be showing here is taken from different parts in the internet. And the most relevant ones are these three ones here, which are the Hazy research blog. That's a blog post from Stanford. Then the annotated S4, which is from Sasha Grush, and also the Mamba primer from him. And of course, if it wasn't for the authors that have contributed all of these things, we wouldn't be talking about this at all. So, all right, so let's start. We're going to start talking about time series analysis. And this might seem a little bit arbitrary at the beginning. But the reason we are starting from here is that time series analysis gives us a very interesting starting place to analyze the different properties that a model that handles long context should have. The reason for this is that there are three important things in time series. First of all, if you have ever seen raw audio, you are going to notice that these audios are recorded at something called kilohertz, right? Which is nothing else than saying how many samples you get per second. And so in a second of audio, you normally would have something like 16 kilohertz up to 48 kilohertz, which means that per sample, per second of audio, there are 48,000 samples. And so if you think about text and you go and look at ChatGPT and all these different things, you are going to see that they have a huge, humongous context length of 32,000. And then you're like, oh, if I want to use this for something else than text, I'm not going to be able to do anything, right? I can analyze maybe half a second of audio, or maybe 1, 2 at best. So this shows the scale in which these models should go and work. The second one is continuity. Different from text. So text is not what I call real data or like natural data, and it's because it's a condensed form of information, right? You don't see text emerging naturally from the universe or something like that. And so normally natural data, they follow some laws, which are given by physics, of course, and everything around it. And so this is also interesting to see the inductive biases that our models should have to solve this kind of tasks. And the last one is very related to the first one, is memory. And well, as I mentioned, you need to keep track of a long sequence. And so it's important how you are going to keep your story in memory, or how your model is going to reason about it. And of course, the first one is efficiency. So of course, it makes a lot of sense that you cannot take quadratic complexity to, like process sequences of length more than 30,000. Otherwise, they're going to wait for a very long time. So what paradigms are there for time series modeling? Well, there are three main paradigms. The first one is the recurrent one. I'm pretty sure you guys are all familiar with this, but yeah, recurrent neural networks have been used for a long time, and they have interesting inductive biases for sequential data, in which they have like this story that's been kept during time, and you are always updating it, and that's what you use for the predictions. And it has very efficient inference because you have this state that has a fixed size, and so when you do inference, you're going to do this in O1 complexity, so constant memory complexity and also constant time. And the problems with those ones is that they're slow to train. You cannot really parallelize them. And they suffer from problems that are very well known, such as the vanishing and exploding gradient problem. We're going to talk a little bit more in detail about each of these things later, but yeah, so that's the recurrent one. Convolutional ones, the problem with those ones is that they have fixed context size, right? When you define a convolutional kernel, you would say, I want it to be size 3. That's what you're going to use, and then your context is going to be determined by how big you make it. The other thing that is bad about convolutional modes is that it's very slow in autoregressive settings compared to recurrent modes, because you're going to need to keep track of your history over time, a little bit like self-attention in that sense. But the good things is that they have local interpretable features, and that they're very, very, very efficient to train. That's the most important thing. When you're doing convolutions, a convolution is nothing else than using the same kernel in a lot of different positions, and so this is trivially parallelizable, and you can use GPUs and everything to speed that up. And lastly, we have continuous time models, which are things like neural ODEs. The good thing about them is that they have this continuous notion of time, and that allows them to handle things like irregularly sampled data, for instance. Or also, if you change the resolution of your data when you're testing, your model is not going to fail like discrete models would. And also, since they have like this continuous framework, it's easy to analyze mathematically, and so that's going to be very important. The bad thing is that it is very slow, both in training and inference, basically because you are solving an ODE during your propagations of everything. Now, there's also a quadratic elephant in the room, which is the self-attention method. And the reason is not between the first three is that it is not really adequate for time series. There are papers that show, for instance, that a set of embarrassingly simple one-layer linear models, they outperform existing sophisticated transformer-based models in all cases. And this is due to multiple things. First of all, you don't have the right inductive biases, because self-attention, they do operations on sets, so you can induce a little bit of like inductive biases by adding position and coding and such. But in their own, like in their framework, it's not something that they have. They're not adequate for long sequences. They're extremely expensive to use, right? But they're also easy to train, right? They are parallelizable, and they have unbounded global context, so that's also something that is very good. Right. So there have been a lot of efforts trying to combine the different properties of these different models. And so very briefly, you have models that are recurrent and continuous, right? You have models that are convolutional and continuous. And so they're going to have the properties of these kinds of families that they are part of. So the recurrent and continuous, they will have a little bit of an enhanced interpretability and would be able to handle irregularly sampled data, etc. Convolutional and continuous time, they would be able to work at different resolutions because of this continuous formulation. They would be able to handle irregularly sampled data, etc., etc. And then you also have recurrent and convolutional. And here I want to call something to your attention, and it's the following. let's imagine that we have a recurrency, a linear recurrency of this type. Okay, so we have the hidden state is some sort of weight that is going to take our previous state plus what we are seeing in the input, right? If we look at this very closely and we unroll this, what we are going to see is that this is nothing else than a convolution. This is basically going to be a convolution between these inputs x1, x2, x0, x1, x2, and a kernel that is going to be given by this: 1 for the last position, W for the second position, W squared for the third position, and so on and so forth, up to Wn, right? Basically, the further you look into the past, the longer this weight would have been multiplied with that particular input. Is that clear to everybody? Great. And this also shows why RNNs suffer from vanishing gradients and vanishing activations, or exploiting, sorry. And is that, imagine that the value of this W is larger than 1. Let's say it's 1.1. And then we have sequences of length 1,000. That's not very long. So the final weight of the last position, it would be 1.1 to the power of 1,000. As you can imagine, that's going to be very large. Now let's take the other side. Let's say that this W is 0.99. Well, if you multiply 0.99 to the power of 1,000, you're going to see that that's also very, very small. So this is only illustrative to show that there is this problem here. But there is also some advantage in this formulation, and is that since you can see this as a recurrence, as a convolution, during training you would be able to parallelize everything, right? Because there's simultaneously a convolution and a recurrence. And so during training, for instance, you can just parallelize everything. And once you're doing inference, say in an autoregressive setting, you can change the mode to a recurrent mode, and then you can do inference in constant time. Right. So what do we have? We have RNNs, which have a theoretical unbounded memory, but in practice, we are always going to see that that's not the case. We have ODEs, which suffer from problems similar to RNNs. By the way, they are also both not really efficient. And then we have convolutions, which are parallelizable, and they have they behave well. But the problem is that they're fundamentally a fixed window model, right? You need to define how big your kernels are going to be. And so they have bounded text, bounded context, sorry. That's going to be, we're going to change that at some point, but in principle, this is what we have. And SSMs, as we're going to see next, the idea is to combine the strengths of all these different models, the continuous, the convolutional, and the recurrent, in a single model, such that you can make use of all these different properties that they have. Questions so far? Yeah.
I have a question about this recurrent form and this convolutional form.
Yeah.
Is there any other interpretations? Usually a convolutional kernel is dependent on the position or relative position, right? And then you have like a basis or maybe a polynomial basis in x. So if x and x squared x to the power 3.
Yeah.
Relative x. But now I see this in w squared w to the power 3.
Yeah.
So it's a very odd way of weight sharing. And
yes.
Weight sharing. I was just wondering if there's any interpretation to this, also from that perspective.
Yeah, that's a very good question. So we're going to talk a lot more about that a little bit later. But the idea here is, what I'm saying here is that all these kind of recurrences can be described as a convolution, but not all convolutions can be described as a recurrence, if that makes sense. And so when you unroll this, you are going to have a kernel that is going to be, let's say, V. Let's say that this is going to be your convolutional kernel. This is the value of V. It's just a scalar. And so what we're going to have is that this kernel is going to look like this, basically. Right? This is going to be your convolutional kernel. right? And that's how you can look at it. But in general, you're going to have convolutional kernels that are much more general. Something like this, for instance, is completely okay.
And the tokens might not be smaller than that.
Oh, right. You're right. Yeah. Other questions? All right. Okay, so state space models. The state space model has existed for a very long time, actually. And it's given by these two equations. So you have an ODE, a linear ODE, that is going to be telling you how the gradient of a hidden state, which is we're going to call this the state of the SSM, X, how it changes based on the previous state or the current state of the input, of the input, this is the input, and the state itself. And the output of the system is going to be given by another matrix multiplying the state plus something that is going to be multiplying UT. Normally, what you're going to see in SSM papers is that, in learning SSM papers like S4 and so on, is that they don't consider this part here. And the reason is quite simple, and is that this DU, you can see it as a shortcut, right? So like a residual connection from the input to the output, basically, which is weighted by this D term. So that's why they don't normally look at it, because it has no impact in the evolution of the state itself. Right, and so the input is a one-dimensional signal. The state is an n-dimensional signal, so you're projecting up. And then the output is also going to be a one-dimensional signal. So basically what you're doing is you are taking your input, you are expanding it into an n-dimensional space, you're doing operations there, and then you propagate back to a one-dimensional signal. And yeah, and so this has been used a lot in, as I mentioned, this is very well known. It has been used in engineering and science for a very long time. And normally what you would do is you assume that you have a system that behaves like this, and then you want to either control the system, like in a automatization, stuff like that, that you like you want to keep your temperature at a certain level. So if it goes up, you're going to change the input so that it goes down and so on, and you are going to sort of regularize the output. Or you don't know exactly what these parameters are, and so you add some signals into the system to see how it behaves, how it reacts to it, and based on that, you can infer these parameters. This is normally what you do in like control theory or like automatization or signal processing, all the different things. But yeah, in deep learning, the idea is that we're going to have this SSM as a black box representation, right, of something that is learning. And what we want to learn is all these different parameters by gradient descent, right? Makes a lot of sense, right? Like also what we did with convolutions. So, oh, this is convolutions. Oh, maybe we can learn them. And then we learn them. And it's basically the same. Yes?
Sorry, in your equation, shouldn't you use x prime for y? Cx prime?
No, I think this is the right way.
Then x prime is not used.
It is used because it's going to tell you how the state is going to change over time.
Okay.
It is the gradient. Yeah, yeah. Oh, sorry, I forgot to mention that. Yeah, it's the gradient. Cool. And the cool thing about SSMs is that it has 3 different representations. So we're going to be able to use SSMs as a continuous time model, as a recurrent model, and as a convolutional model. And as you see, this is already quite powerful, because this means that we can train in parallel, for instance, and then we go and infer in a recurrent mode. We can analyze the properties of the model. We can do a lot of interesting things. So let's start analyzing the different types. We're going to start with the continuous mode. Now, the continuous mode, we already saw it, is this one here. And basically what this is saying is that there is a function, that SSM is a function-to-function map that maps U, the input, to Y, the output. And it's parameterized by these different matrices. And this representation is not really useful in practice, let's say it that way. It's mostly used for theoretical grounding and understanding what is happening and, you know, coming up with initialization techniques and stuff like that. We also have the recurrent mode. The recurrent mode is basically going to take the SSM, this neural ODE, and it's going to basically discretize it, because when we are in an SSM and in a recurrent setting, what we have is a discrete input, and we want to map it to a discrete output. And so what you would do is you use techniques from discretization in neural in ODEs and stuff like that. And so you can define, for instance, these different matrices as the values shown here. Now you have a different, an extra parameter here, which is this theta, which basically is telling you how big the steps are that you're taking in your discretization. There are different ways to discretize. Here, it is using the bilinear transformation, but you normally also would see this exponential, which is, if you solve this, you're going to see that actually this is going to have like an exponential of theta x somewhere. And so, yeah, but this is easier to handle, so that's why people do it this way. And so going back to your question, now we see here that indeed there is this how do you say it, change in the x is given now over time, and so that shows you that this is basically computing how your state is changing over time, this first equation. Great, right? So we can use this in a recurrent mode. Unsurprisingly, we can also do the same for the convolutional mode as what we did in the introduction. So we have a state that is given by these different formulas, right, at different positions, right? So we have basically, if we look at this, at time 0, we're going to have B 0, B, C 0, and then for time 1, we're going to have the A be multiplying 2 times, and so on and so forth. And so when we look at the state that we have at each different time, each different state, a point in time is going to be like this. The x0 is going to be bu0, then x1 is abu0 plus bi1, and so on and so forth. So it's basically the recurrence that we were discussing. And the output is going to be given by this multiplied by c and d in some cases. Does it make sense? And so that means that we can compute a convolutional kernel based on this formulation that is going to be given by this. So basically, if we treat everything as a scalar, we're going to have a convolutional kernel that is going to be CA to the power of the number of steps times B. And of course, this also holds, so this is going to be very important later. Questions? Yeah.
Is there then ever any instability how you're raising A to the power of steps?
Yeah, there can be a lot of instabilities, and we're going to discuss that in a lot of detail. Yeah. More questions?
Yeah, I wanted to ask about the vanishing exploding gradient from this.
Yeah, we're going to talk about that. Yeah. All right. So basically what we have is that SSMs are, I'm missing one here, but in practical settings, what we have is SSMs are mixes, or are models that are simultaneously convolutional and recurrent, right? And what we're going to see is that we're going to have models that are purely recurrent, like Mamba, or purely convolutional, like CKConv and Hyena. And each of these different models is going to have a different, like they're going to have different properties, and they're going to be useful in certain settings, and so on and so forth. Right. So what are the limitations? The main limitation, as you said, is that it can have unstable dynamics. And what I'm showing you here, maybe I can. Do I have a pointer or something? Not really. Okay, I'm going to use this one. So what I'm showing you here is that if I have a random initialization of A, we're going to see that A is the most important matrix here, right? Because it's the one that we are multiplying by itself a lot of times. So if we set to random, our model is not going to work or learn that well, right? But if we set it to proper values, we're going to have very good accuracies and very good memorization. The other thing is the convolutional mode. If you look here, I mean, with the scalars, fine. There is no problem. This is a multiplication. That's OK. But if we look here, all of these are matrices, right? And so if we're multiplying this matrix, which is n by itself, n times, this can be very expensive if A has no structure, right? Yeah?
Hey, what's the typical value of L in these experiments?
Here it is 780. Yeah, it's relatively small. It's MNIST, and then you just flatten it, and then you predict the output. But these models have been used in things like million length and stuff like that. Yeah. Questions? No? Right. So if we want to multiply all of these things and we want to get to the recurrent mode, to the convolutional mode, well, it's going to take us a lot of time to get the convolution at all. And so we are going to need n square L, where n is the size of the matrix, times L. L is the length of the sequence, operations, and NL space to be able to compute this, right? So this is going to be very, very, very expensive. And so this is not very useful. And this is why SSMs have not been used that much up to recently. And basically what S4 is doing is it is proposing different ways to alleviate these two problems. Questions so far? Everything's clear? Maybe online, I don't know if. No questions? No, okay. Yeah.
The kernel size quickly gets really big.
Mm-hmm.
They said, okay, because I'm normally used to having smaller kernel sizes with multiple layers instead of having two consecutive.
Yeah, good question. We're going to talk about that a lot as well. So all the kernels that are used here, in all we're going to see are global. Basically, because when you're using self-attention, you have two properties, right? You have global context and you have input dependency. And if you want to replace self-attention with something that is as powerful as it is, you should at least have these two components. Otherwise, you're always going to be more constrained than the other method. And so it takes, actually, the CKConv paper, that's a paper of mine. And at that time, that was the first paper that proposed to use long convolutions. And at the time, it was very difficult to convince people that we should, use global kernels because people are used to very small kernels and locality, et cetera, et cetera. And so I had a very hard time getting that. But the idea is that these kernels can always be small if they need to, but at least they have the possibility to be very big. And if you were to compute the convolutions on the space-time or on the, let's say, the spatial domain, then this would be very expensive because you have a very big kernel and then you need to do padding and all these different things, right? But you can actually rely on Fourier to go to the Fourier domain and do the convolution there. And there what you're going to see is that you can do this in n log n, L log L time. So that's very, very cheap comparatively. Right. So the Fourier convolution theorem basically says that a convolution in the spatial domain is a multiplication in the frequency domain. And so if you go to the frequency domain and back, multiply there and then go back, you're basically doing the same operation, but now you can do it much faster. Yeah.
The global property being important, but also input dependence.
Input dependence is important.
Yeah.
Input dependence is that the kernels that you're using or the mappings that you're using change in terms of the input.
Okay. Yeah.
Right? And that's something that convolutions don't have because it's just a kernel that you learn. And so if the input changes, it's going to always be doing the same mapping. And self-attention is very powerful because it has these input dependencies as well. Okay. Right. So a small disclaimer here. I'm going to put also the slides online so you can take a look at all the details later. But in interest of time and everything, I'm going to give you my very high-level descriptions of everything. All the details are in the slides and in the blog posts. But you know, like I'm gonna take you through a lot of different things, but I'm gonna try to explain it very, very simple so that it's easy to understand what the core is. So the S4 paper, it proposes two things. It uses an initialization with Hippo, which is gonna solve the problem of the vanishing gradients. And then they also proposes to use a certain structure to the matrix A, such that you can compute the convolutional kernel very fast. Basically, those are the two big contributions of S4. And so let's talk about what we want to do in terms of maintaining memory. So Hippo stands for, what does it stand for again? Optimal polynomial projections. Yeah, well, the idea is that you are going to project your input to a certain space, and you want this approximation to be as good as possible to memorize the whole sequence that you have seen so far as good as possible. Basically, that's what you want to have, right? If you see this in a recurrent mode, what you want is that once you have seen, since you have a fixed state, right? What you want is that you want to learn or like keep in memory as much information from the input as you can, save this information very well in your state, and then you can rely on this information to make the next prediction, right? If you don't do this properly, then your hidden state is going to be basically very redundant. So it's going to be wasting a lot of the possibilities that it could have, right, in terms of memorization. And so they formulate this as the following. So you have an online function approximation. Basically, this is what you want, right? You are seeing a sequence during time, and you want to update your memory such that the projection, such that the memory, such that your input so far is memorized as good as possible, right? And the idea here is based on two things. So given an input function, f, which is one-dimensional, we're going to project it into an n-dimensional space, right? This is what this B matrix here was doing, right? It's taking the input and it's projecting it up to a hidden to a certain state. So yeah, given this input function, we want to maintain a representation that lives in Rn, right? At all times, such that it optimally captures the history of f from 0 to the current time. And so basically what we're saying is, we have an input, we have n dimensions, we want to take this input, project it into these n dimensions, and do this as good as possible, right? Optimally. And if we want to do this, we need to define two important things. How are we going to assess that an approximation is good? That's very important, right? We need a measure to say, hey, this is better than this one. And we also need a basis for this hidden representation in which we're working. And so, high order, that was the first thing that I was missing. And so the idea here is that if we think about this problem, let's go back once. If we think about this problem, and we think about how we could structure this n-dimensional space such that the coefficients that we're using are used as good as possible, it makes a lot of sense to use an orthogonal basis, right? Why? Because if we have these two vectors, right? Sorry, this two-dimensional space, and we have a vector here, then we are going to have one coefficient here and one coefficient here that is going to tell us where exactly this vector is, right? This is the beauty of orthogonal basis. If we do not have an orthogonal basis, this information is going to be coupled. It's going to be entangled. And so you're going to need for this, in a sense, like you're going to be, you're not going to be able to use your parameters as good as possible in comparison to this non-orthogonal case. Does it make sense? Yeah. So that's what they did. They say, oh, it makes sense to use an orthogonal basis. And so for this project, for this problem, they relied on tools from approximation theory and also orthogonal polynomials, because it has been explored a lot in like like classical books on how you kind of store a certain input into, or a certain signal in an n-dimensional space in an optimal way. You know, like we think about it, this is a quite a very general problem, and so people have worked on this a lot. And so what we need to define is the selected measure that we're going to use, right? How are we going to measure that something is better than the other? That one approximation is better than the other. And we are going to use orthogonal polynomials, basically, for those two things. And so now we can define different measures, right? We can say, for instance, that what we care about is only recent history. So we're going to decide that how good our approximation is not going to depend on the whole history, where we're going to say, please only look at the last theta values. And then what you're going to do is, I want to approximate these theta values as good as possible. Yeah. There is another one, the translated Laguerre, which basically says, instead of having a uniform weighting of the past history in this window, I want to have a measure that says that the importance is going to decay exponentially. So basically, your weights, how good your approximation is going to be depending on how good are you able to preserve the recent past more than the past. And then you have another one, which is the one that actually is used everywhere, and is that you say, I don't want to consider a window. I just want to consider my whole history. And I want to consider each step on this whole history with equal weight. So basically, what this means is I want to preserve my whole history as good as possible. And perhaps unsurprisingly, that's what works best in practice. And so if we look here back, oh no, it's, yeah. If we look here back, this is going to be the hippo line, which is the blue one, which you can see that it's definitely much better than having these random values. Cool. So once we define this measure and we define the polynomial basis, right? What we're going to have is that we're going to solve this, here it is, this ODE. And surprisingly, this ODE here has a very simple solution. Well, relatively simple, a very structured solution. So it means that, sorry, I forgot to mention something important. Why do we have this? Is because you don't want to take any step. Let's say that we're at step 10, and we have a certain projection of this whole thing into this into our space. Now we are in step 11. The trivial solution, or the easiest solution that you would do, is I project everything again back into my history, and then I'm done, right? But this is, of course, very expensive because you're going to need to look at the whole history again, project it again. Everything here is about efficiency, so you don't want to have this kind of very expensive steps. And so they formulate an ODE, which is going to tell you how you should change your past coefficients such that your new coefficients are optimal given the whole history and the new coefficient that you're getting, right? And this is super important because it gives you a structure of this A matrix, right? Which is basically doing the same as the A matrix that the SSM was doing, that has a very, very good, very well-defined structure. So it has like, it looks like this here. So this is, if you put it into code, it's going to look like, yeah, like some negative values that are large, depending on the values here. And if you see, this matrix also has a lot of structure. It's 1, 2, 3, 4, 5, right? So it's like a diagonal like this. And it has some values here that are combinations. And all of the upper part of the matrix is 0, which is actually quite cool, right? So now suddenly you are trying to approximate in this online on this polynomial basis. And now you found a way in which you can dynamically change time by time the projection that you should have such that everything in your history is going to stay optimal up to whatever point in time you have. Yes?
So these coefficients, I should interpret them basis coefficients relative to the polynomials, as in I can reconstruct the signal from these coefficients.
Yeah, exactly. Yeah. So no, yes, but no. So the A matrix is the transition, right? So this is how your coefficients are going to change over time, and the coefficients themselves are the state. If that makes sense.
Yeah, maybe so.
Yeah. So you. So you have C time t, right? And then for C T2, let's say, which is T2 is larger than T, then what you have is that this is going to be like the matrix multiplied by this plus some part, I think it's also called B, that is given the input at this new time T2. Okay. Yeah. Right. So this C is the projection, the coefficients of the bases, and this A is going to tell you how you need to change that over time.
And this recurrence comes from the polynomial form of the basis.
Yeah.
This is the A-matrix that we're looking at?
Yes. Oh, sorry, I didn't say that. Yeah, this is the A matrix. So this is basically this in code for a 5x5 state. Yeah. So the state is basically n, right? And the matrix transition is going to be n by n. Yes. That's right. Yeah. And so if we define, for instance, this windowed thing, we're going to have a different solution to this ODE, and so the matrix A would look slightly different. But I'm only showing you this one because this is the one that works best, and also, yeah, like if you think about it, is the one that makes the most sense, right? You would like to preserve your whole history and not only your recent history in the most general setting. Yes.
So it seems they derive this metrics from the perspective of, okay, let's derive the transition matrix, which makes the most optimal memorization.
Mm-hmm.
But previously we talked about stability, that we want to impose some structure to be more stable.
Yeah.
Is it inherently memorization equals stability?
Basically, yes. Yeah. And if you think about it, it makes a lot of sense, right? Because if you have a hidden state that is able to reconstruct your whole history, that means that you have shortcuts to the past history, right? In a sense. And so when you are doing this recurrency, you're going to be able to like propagate information better. That's a little bit the intuition here in hand-wavy terms.
Yes. Coming from the fact that you have an analytic form of this A matrix.
Yeah.
You don't have to do this recursive computation.
Yeah. So
and it's large with history length. Yeah, and you do this recursively. Wouldn't you still have like exploding or vanishing coefficients?
I mean, you're not going to have vanishing gradients. They show in the paper that if you use this kind of recurrency, when you calculate the gradients, they decay not exponentially, but I think it was quadratically or polynomially. Yeah. So it's less than exponential, and so that means that you can have information going through the past. However, it is worth saying, of course, that we are doing approximations. So nothing's going to be perfect, right? And so, for instance, here, I'm showing you, this is some signal that we want to approximate, and they use this kind of approximations to approximate this signal, which has 1 million time steps. And if you use an STM for this, you basically can't. And if you use this hippo-leg S formulation, you can get much better approximation. So it's going to be 0.02 for hippo and 0.25, which is basically almost, I mean, it's not random, but it's not very good for an LSTM, right? And so this is also going to be very important. We're going to discuss this later, that since we're always doing approximations, we're going to inherently lose some information from the past. And so in a sense, this is going to be one of the shortcomings of having RNNs, which self-attention does not have, right? Any other questions? Yeah.
Yeah.
I'm trying to develop some sort of intuition behind why this model memorizes the past or what it does. In case of attention, basically what we're trying to do is that even embeddings for two elements on the sequence, which can be like sometimes far away from each other, want to see how much, how important is this element from the past, let's say unidirectional case, how important is this element for the past for, let's say, my embedding here in at the current time step. We sort of develop different, well, we have a softmax basically that tells us, okay, this is more important, this is less important.
Yeah.
From what I understand, and please correct me if I'm wrong, because we probably have, here we are trying to memorize all of the past with the same weight, with the same...
Yeah, so there is basically a very big difference, and is that in self-attention, you're not compressing your history, right? So basically, when you have an input of size like this, right? And you're doing self-attention, what you do is you compute a very big matrix that is going to compare everything to everything, right? And so let's imagine that we are here in the next step. If I want to calculate some values for this one, I still need to have my whole history, right? So if I have, let's say that this is 1,000,000 length. So for this computation, I'm going to need to do a softmax over some, like over a matrix or like a vector is going to be 1,000,000 on which I'm going to do the softmax, right? Let's imagine that this is 10. Now the value, the vector on which I'm doing the softmax is 10, right? So here you're not doing any compression because your history is always kept in memory. That's why self-attention is so expensive. The other thing here, in the RNNs, or in this formulation, the difference is that at some point, right? Let's imagine that this is the new token, right? To get values from this, the only thing that I'm going to look is I'm going to do is I'm going to look into this latent representation that I have that has fixed size, and based on that, I'm going to know what this is going to be, right? And so the question is, how can we structure this hidden latent state, such that the information that is inside it compiles as much information as possible from the whole past. Whether it is 10 or whether it is 10 million, right? If you see here, since you're always compressing this whole history, the fixed size and everything, this is always going to be constant in terms of memory, right? Because you're always multiplying with something of the same size. In self-attention, this is going to grow, right? So that's where the difference is.
I understand the computational implications. I'm curious if the SSMs sort of lose that information, lose the ability to distinguish which of the previous tokens is the most important for my next, for the token I'm currently considering.
Yes, they're gonna lose information for sure, as soon as the fixed site, let's call this n, right? As soon as n is smaller than whatever it is here, you are gonna lose some information, right? Let's imagine that this is length 7, and so basically, let's take a look at our hidden space. So this is gonna be, let's say this is 10 and this is 10, right? So we want to preserve the whole history. This is super simple, right? We just have whatever value there is here in the diagonal, and we're done, right? Up to here. This is 7. This is the length, right? In this case, what you say, we can do that directly, right? We could know which position it was and which each token was there because we know exactly what it was and so on and so forth. So everything is here preserved. But as long as this is, let's say, much more, in this trivial case, trivial example, let's say it's 14, I cannot use this anymore because I could at most compile this to 10 different positions, right? And so I'm going to be doing approximations at some point.
Yeah. I was asking this question about paying attention to important or non-important stuff because I guess this idea that we can discard some tokens as helped us scale transformers to very long sequences.
Mhm.
I'm curious about the context length for those models.
Yeah, so what we're going to see in Mamba is basically that it's going to be using some sort of gating here to preserve or to decide which information gets projected to the hidden state or not. So in that case, you can disregard information that is not as important, and then the state is going to keep only information that is very important. Whereas right now, because nothing is input dependent, right? You are always sort of storing the whole context given on your the measure that you give. Yeah, and so you're going to have a gist of the information, but of the history, but it's not going to be perfect.
Like with LSTMs.
Right, in a sense, yeah. Yes.
Does that only work for data for time series, where every sample is a scalar value, or it's going to work for general sequential data? Every sample can be a vector.
It also works. It also works for multivariate stuff. Yeah. What you're going to do is, well, it's just as with convolutions. What you're going to do is you're going to take a lot of these different ones, you put them in parallel, then you mix them. Right? Like let's imagine that we have an input of size 10, and so we're going to have like a way to interpret this is a CISO system, which is single input, single output. And so what you're going to do is you're going to have 10 different of these SSMs working in parallel. And so at the end, you're going to have 10 different projections of this, right? And for the output, let's say you want to have 512 channels. Well, then what you have is that you mix them all together, and then you get the output. Normally, this would be larger than this, but you know, it's yeah.
Trying to wrap my head around this, where do these orthogonal basis functions coming into this matrix? Are they parameterized?
Yes, they're parameterized under the hood. Basically, so this solution here already assumes that. And so once you use this matrix for the projections, this is going to impose like this projection structure onto this matrix, onto the hidden state, sorry. Yeah.
Maybe if it's completely at some point, we have some maybe take a.
Okay. Oh, it's already 10. Yeah. Sounds good.
Yeah.
Okay.
Grab the car.
Right. So let's continue. Right. So I think we're having something very dynamical here. So I like that a lot. And so it might be the case that I'm not going to be able to finish all the slides. But if that's the case, then we can just do a part 2 or something at some point. But I think it's much better if we, like have this kind of ongoing discussion and learn a little bit more about all the details than just rushing through slides. If you agree with that. Otherwise, I'm going to rush through slides. Okay, cool. Right, so we discussed how to solve the vanishing problems with this sort of initialization. By the way, something that I didn't mention is this is how you initialize the matrices, but these matrices are also learnable, right? So you just give a good starting point, but if you want to deviate from that, then the model is going to do it by itself. And now the other problem that SSMs had was computing the convolutional kernel, right? Which is very expensive. And so they came up with a very, very interesting way of solving this. So the idea is that you want to compute this kernel, right? And if you do it naively, you're going to need n square L operations and NL space. But if we think about A, and if let's imagine that for a moment that it has, 1 second. Yeah, let's imagine for a moment that it has structure, so that it's diagonal, that the matrix A is diagonal. Well, if it were diagonal, we could compute the multiplication of matrices very, very, very fast, right? It's just multiplying the diagonal components and you're done. That would scale much better. And well, this A matrix is not diagonal, but it does have a lot of structure, right? So it has like this diagonal here, and it has like this other part here, and it has only zeros in the upper part. And so they make use of that structure that the matrix has to define an algorithm that is going to compute this matrix much more efficiently. So basically, in big details, what they do is they say that this matrix is going to be a normal matrix plus a low rank matrix, right? And with that, you can do a lot of cool decompositions. So briefly, what you can do is you can go to the Fourier domain, right? And you can think of this as some representation of a system. And so you can, in the Fourier representation or the Laplace representation, you can think of this as a system, right? Like the original representation of a SSM was, we have a system that we don't know the parameters of, etc., blah, blah. So you can go to this domain, and there you can try to generate this matrix function, or the function, the generating function of this system. And so they do this by computing a Cauchy kernel. This is all very detailed if you look at how this is formulated. But the idea is that, yeah, you can go to some sort of alternative representation of the system due to its structure. And then based on that, you can compute the kernel very fast. And what they do is with this, with this kind of alternative representation, they can reduce the computation of K from n square L operations and n L space to n plus L operations and n plus L space. Oh, well, when you want it to stay still, then it doesn't, but the rest of the time it does, eh? Right. Yeah, so this is very complicated. I don't want to get into much detail here, but you know, like they found a way. The Fourier domain is always nice, and so they found a way to compute this very fast. And now that you have this n plus L operation and space complexity, you can compute the kernel relatively fast, and you don't have problems with the memory anymore. And so that's how S4 was born. With these different changes to the SSM structure, they were able to scale this up and get very good results. Yes. You raise your hand first.
Yeah. So the big plus of attention mechanism is that it's basically a dot product and a lot of dot products.
Yeah.
And the thing about dot products is that they scale very well for GPU architecture.
True.
The question is, does this scale very well to GPU architecture too? I don't understand this algorithm. So this is why I'm asking. Yeah. Is there like a lot of conditional branches or some weird stuff that GPUs wouldn't like here?
Right. Yeah. So they have a low level implementation of this, and they do it. I don't know. I'm not sure if they do it in CUDA or in Triton, but they have a low implementation of this. Now note that this is only for the computation of the convolutional filter itself, right? You still need to do the convolution. And you raise a question that is very important, and is whether we can do, for instance, FFT convolutions very fast, right? Matrix multiplications, they are nice and everything, and you can do them in parallel very, very well, but we don't know if that's the case for these other kinds of operations. But there is a paper that is called Flash FFT-conv, and what the paper does is basically an analogous of flash attention, but then for convolutions in the Fourier domain.
Flash attention is fast.
Flash attention is fast, and Flash FFT-conv is also fast. It's based on relatively the same kind of idea of splitting in matrices that are like 32 by 32, and then you can just parallelize everything. Yes?
Does calculating this convolutional kernel in, let's say, the Fourier domain, does it place any additional constraints on the A matrix? You mentioned, so HIPPO gives you initialization from A.
Yeah.
You can still optimize the weights freely, right?
Yeah.
Does this place any additional constraints on which weights you can or cannot optimize?
No, not really, because so here what you have is that you have this A matrix, right? And this matrix is like separated in different parts, but that obeys the structure of the matrix. So in a sense, indeed, it has a little bit, so you cannot, like in principle, if you make all of these learnable, these coefficients could be non-zero, for instance, at some point. Right now, when you do this kind of decomposition and you assume that this is going to be the structure, then you're always going to have this structure. But yeah, it doesn't seem to be a disadvantage or anything. Yes.
Maybe the main question about what you said about fast convolution. So, right, we can do fast convolution in Fourier domain, but aren't we assuming like circular boundaries? And here, as I understand, we need to have causal convolution.
True, both of them true. So when you do causal convolutions, well, it's okay. The other thing is you can also do causal convolutions in the Fourier domain. The difference is that, so the question is basically saying this: when you go to the Fourier domain and you have an input, you assume that this is a periodic input, right? And so if we are doing convolutions here, in principle for this point, you're going to be seeing the future, right?
Yeah.
And that's going to be a problem in autoregressive settings and in causal settings. But this can be solved very, very easily. What you do is you path. And this is your signal now.
This one's probably this one.
Oh, yeah, sorry. Thanks. Oh, yeah, I realize this is difficult to see. Okay, so what you can do is you just path the beginning of the sequence. And so now your function is going to be this, right? And so if you look at this point, you're going to be looking at zeros and this.
Oh, makes sense.
Sorry, not this actually, this. And so at each point, you're going to be only looking zeros and plus. Yeah. Cool. All right. So the S4 model initializes, to summarize, it initializes the SSM with an A matrix set to the hippo matrix, right? And they decompose it into these vectors that assume that structure of the matrix A, and that's what is learned later. The S4 defines a model from 1D sequences to 1D sequences. And so if you want to handle multiple channels or multidimensional things, you do the same as what we do in deep learning all the time. You define H independent ones, and then you mix them. And all here is linear. And so if you want to induce nonlinear behavior, you also do what we do in deep learning. You put nonlinearities in between. Cool. I also mentioned that S4 is a CISO system, which is single input, single output. But there you can also formulate this differently. You can also formulate a multiple input, multiple output SSM, which basically considers all of the channels of the input, makes them all together, and then you get n channels at the output as well. The problem here is that you cannot then have the recurrent mode. Sorry, have the convolutional mode. And so you need to implement other things to be able to run this efficiently based on parallel scans, which also Mamba uses. And also interesting is that there's another paper called S4D, which shows that if you approximate the matrix A with only a diagonal matrix, this also works. So that's also interesting. It works well, but it doesn't work as well as. Right. And since S4, its emergence, it really broke everything else down. So yeah.
Previously, you said that S4 decompose everything and efficiently calculate any linear time, linear space. So it's also linear time, linear space.
It's even faster because you don't need to do this anymore. So if remember that if you have two diagonal matrices and you multiply them together, you just only need to multiply each of the diagonals with themselves, right? And so if you want to compute this matrix here, it would be just computing each of these components with itself times n.
Yeah, it's true, but the S4, what's the difference in complexity there?
You mean for the S4D, the diagonal version, or?
No, S4.
Yeah, so the complexity here you mean for the computation of the kernel? Yeah, it's when you use these tricks, it's O n plus L for operations and space, both of them. And if you do this naively in the spatial domain, it would be n square L for operations and n L space.
Yeah, okay, I understand. But if it's just diagonal, then it's don't you still need n or linear complexity of
I think so.
operations?
Yeah, I think it would be L.
Just
It would be L. Yeah. Yeah. Right. Yeah. So yeah, as you can see here, transformers. There was this long-range arena benchmark, which is not really used anymore. These tasks have been kind of solved. And yeah, these sequences here can be 16,000, for instance, and so on. And with S4, it went nuts, and all the transformers and stuff, they were not really pairing with it. So this was, I think, this was a very important breakthrough. But there was still something missing, and is that it was specifically on text. This was lagging behind other methods like self-attention. And yeah, this inspired other works in like both the recurrent mode and the convolutional mode that we're gonna discuss next. But before we do that, I have a question for you. The question is, we know that the S4 that it weights the whole pass with equal weight, right, for the approximation. And so if I tell you, but this is only for like the recurrent mode and so on. So I have a question for you. What do you think the convolutional kernels would look like? Right? Remember, we had the convolution, we had the recurrent mode, but we also have a convolutional mode. So what would the convolutional kernel of such a system look like if we are weighting the whole path with equal weights and so on? Any candidates? At least like the rough form? Like you say that the kernel would be, so this is a kernel, so the kernel would be something like this, let's say.
Yeah.
Okay.
The kernel would be the size of the input.
Yeah, it would be the size of the input. Yeah.
Decay 1 over L.
So you say, okay, this is the last point of the kernel. Okay. So you say something like this. Okay. Interesting. Any other options? So David, you say this one. Why?
So you say.
Oh wait, sorry. Yeah.
Maybe like the lower one, but flip.
Invert. But this is the last point. This is t and this is 0, right? So the kernel is going to be like this. And you say it would be more like this. Okay.
Add one at a sinus.
A sinus, yeah, sure.
Yeah, we just had a different form.
Something like this. Okay. Okay. Why do you think this one?
So you said that S4 weights all time steps equal.
Yes.
So I think the convolutional kernel that does that would be a constant one.
Yeah, makes sense. Okay. Eric, why do you think this one?
Yeah, it was based on this multiplicative stuff that you explained before, and if you maybe in the polynomial basis, when you wait to keep this stable, is that you truncate it or let it decay over time.
Interesting. Okay. This one?
But because maybe you have like the vanishing gradient problem, you just need a way to pass exponentially more in the future.
Okay. And this one? Is there any?
Yeah, once in a while I want to remember something, the rest doesn't really matter.
Okay. Right. So this is inverted, by the way. So it's this one. So you are right, Eric. This is the way that the kernels would look like. Which to me, I would agree with David. If you are looking for like preserve the whole path, I would go for something like this, right? But it seems that due to the recurrences and the fact that you have a hidden fixed size space, your kernel is gonna try to do something like this, where implicitly, the higher frequencies are going to be multiplied with the latest elements, and it's going to decay over time in the past.
Aren't all filters supposed to be like composed matrices?
What do you mean?
I mean, like we have this state space equations where we have matrix A, B, C, and then we compute the kernel from this A, B, C matrices. So I solve that. We have a matrix.
That's a very good question. No, but I understand your question, and the reason is that I can just.
Or just one dimensional.
So remember that we're doing operations from a one-dimensional input to a one-dimensional output. We only have this thing in the middle that is big. And so if you want, once you compute this like a recurrent, like a convolutional thing, you are implicitly going to jump over the state thing because it's compiled in the kernel. It collapses to one dimension. Yeah. Yeah, because you're computing this y, which is one-dimensional. Yeah. Cool. So yeah, this is very weird. Honestly, I don't really understand this completely. Like, I guess like Eric's take is the right one in terms of why this happens. But I think this clearly gives something, clearly shows something, and is that the kernels that are being used here are heavily constrained. And so in principle, you should be able to define convolutional kernels or convolutional models that are much more powerful than this. And that's what we're going to talk about next. Any questions from this part? No? Well, I hope you learned something about S4 and SSMs. Now we're going to talk about other things. So we talk about SSMs. Right. So small summary of what we saw last time up to this point was that, well, we have SSMs, right? And SSMs are models that are both convolutional and recurrent, right? But as we might expect, there is also possible to have models that are either completely convolutional or completely recurrent, and that still have the properties of the nice properties that SSM had. Basically, also, which are, or like the main property of SSMs is that they can model long context. And so you can also do this with different models. Right. So there were multiple works trying to improve the, or like enhance the abilities of SSMs to model text. That's something that SSMs couldn't do very well. And so there were multiple tries on this. One of the papers that tried to do this was H3, and they investigated how S4 was able to do associative recall. Associative recall, very briefly, is a task in which you give a string of inputs, and you need to predict the value of the last that is associated to the last key in the sequence. So here, for instance, you have A2 and then a sequence of things. Then when you are queried with an A, you should give as output 2. The thing is that for each of the sequences in the data set, the assignments are going to be different. So for the next sequence, it could be A5, and in that case, you would need to recover a 5. And so if you don't do this in an input-aware manner, you are not going to be able to learn this in the weights of a neural network, right? And they try to solve this with some interesting, some modifications to the architectures. What they did was to use an SSM to model long context, but also have a shift SSM, which basically would take the token from the last point, from the past time step, and then put it back into the present step. And with that, you can do comparisons between what you have in memory and the current token. And with this, they were able to solve a little bit of the task. But that does not really solve the problem. And the reason it does not solve it is that the key thing that is still missing is, or that these models were missing, is the input dependency part, right? Which is basically the thing that allows transformers to do this kind of tasks very easily. And so there was a paper called Hyena that asked or like tried to improve the in-context learning capabilities of general convolutional models. A little bit trying to simulate the abilities of self-attention, but then without the cost of using self-attention. And in the associative recall task that I just showed, this Hyena model was able to even outperform Transformer. Let's say that they were just as good. It could be a little bit of noise, but it's definitely much better than using normal convolutions or H3 because this model is in fact input dependent, at least in a sense input dependent. And so the idea of this Hyena hierarchy is that when you look at attention, you have this, it's actually doing a linear mapping with some sort of function that depends on the input, right? And the key thing is that the thing that is multiplying the input, it's input dependent. So it's also a function of X. And so if you were to plot the attention matrix, you would see something like that looks like this, where for each different column, you have something that is slightly different, right? If the model was not input dependent, you would have something that looks more like this, where for each position, you are using always the same mapping. In this case, it is a convolution, so it is shifted by one at each position, but basically it's always using the same thing. And so the idea of Hyena is to provide convolutions a way to have this input dependency by using some sort of recurrency that is depending on, or that is composed by convolutions and gating. So basically what you have is you have a convolutional filter that is very long, and then the output of that, of a convolution with that, the input with that kernel is going to be gated, and then you do this a few times, and that's going to give you a mapping that is going to look like this HU here. And as you see, this is also input dependent in that it is not using the same mapping everywhere. It's actually using a mapping that is depending on the position of the input. So yeah, going back to the recurrency, there are two components here. One of them is the long convolution that is used, right? The kernel H, and the multiplicative gating that is happening with this. And what they found in the paper is that, well, of course, because of this, the operation is global because it's using very long kernels, so it has the ability of long context, just as SSMs, but it's also input dependent due to this recurrency, and as you can see here. And in the paper, they find that having a recurrence of order 2 or 3 is sufficient. You can imagine that if this recurrence was very large, then this would not be very efficient. And so that's also like a key thing there. Now, the question that arises here is how to parameterize the convolutional kernel. And yeah, in the paper, they tried different ways to parameterize the kernel. So they tried conv1d, which are explicit convolutions, Fourier neural operations, which are some sort of convolutional kernels that are parameterized in the Fourier domain to allow for longer context. H3, which is the model that I showed at the beginning, some other parameterizations, and also CKConv, which is a parameterization of the convolutional kernel based on a Fourier or on a feed-forward neural network. And what they found was that, yeah, they were comparing these different kernels to see which one would work best in this kind of scenario. And they found that CKConv and Hyena, which is basically a CKConv combined with an exponential decay modulation, I'm going to talk more about that later, was the best option. The other models that they had, like H3 and so SSMs, etc., were not working as well. And so let's talk a little bit about this continuous kernel convolution parameterization that they use. So the idea here is that when you're learning a CNN, the most important thing is how you are parameterizing the kernels in the CNN. Reason being that when you learn a CNN, you are basically trying to get the optimal kernels that solve a certain task, right? And so if it's very weak, then you're only going to be able to do weak operations. So let's imagine that we have this kernel here with 3 positions, but we restrict the 3 positions to be equal, right? So we would have 1 parameter. then all the operations that we could do in convolutional form would be kind of small means of the neighborhoods. And that's really not that expressive at all, right? It's only to show how important it is that we think about this. So how are kernels normally parameterized? They normally are parameterized as a sequence of independent weights. So if you have a kernel that is of length 3, you will need 3 parameters for that. If you have a kernel that is 3 by 3, then you will need 9 parameters for that. And this has quite some limitations. The most important ones being, like, since I need to have the number of parameters of my network tractable, I can only have very small kernels. That's number one. The second one is that since you're learning these things during training, you cannot dynamically append weights to the network or to the kernel if you need them. You need to define a priori how big these kernels are going to be, right? And so that means that there are very big concerns regarding the long context abilities of the network, and also how to define these convolutional kernels. The idea here is that you replace the discrete representation of convolutional kernels with a continuous representation. And the way that you do it is to have an MOP, feed-forward network, right? That is going to receive a position in the kernel and is going to retrieve the value of that position at the kernel. So basically what you're learning is a continuous representation of the convolutional kernel that you're going to use, that you're going to sample to do the convolutions. And it has interesting properties because it allows you to have arbitrarily long inputs, to handle arbitrarily long inputs. Because right now, like if you have a longer input, you can simply sample more positions and then you put them through the kernel and you're going to have the exact same kernel, but then at a larger scale. And it doesn't cost anything to do this, right? It doesn't cost additional parameters because the parameters of the kernel itself are given by the parameters of the network that are parameterizing the kernel. It also has other cool properties because due to it being a continuous representation. So something that is also very nice is that it would generalize across resolutions. Because if you have an input, let's say this cat here, and a kernel that is continuously parameterized, if you were to convolve at different resolutions this kernel with the image, you would have roughly the same output, but then at a different scale. And so this is interesting because that could allow you to train networks, for instance, at low resolution first, and then start fine-tuning them in higher and higher resolutions. And that's not something that you can do natively or like very easily with normal CNNs. And another property, which is very, very important, is that in contrast to SSMs are purely sequential models, and actually only causal sequential models. They cannot really look into the future by default. In contrast to that, this parameterization can be easily extended to multidimensional data. So you can easily go to 2D or 3D, or you can also do or you can look into the future, do this kind of bidirectional reasoning. Now, one important thing to say here is that the main assumption of these things is that the neural network that you're using to parameterize the kernel is going to be able to model all functions possible. But there is a lot of research showing in the neural fields literature that normal MLPs with ReLUs and CLUs, etc., would only give low frequent approximations of the input. And that's known as spectral biases. But luckily, since this has been studied so extensively in the neural fields literature, we can rely on them to find a good parameterization of the convolutional kernels. And so here, by using sirens, we're able to get very good approximations of all these different functions, even to random noise. This is here random. Whereas with ReLUs, you only see that they have very vague, low frequent approximations of what you have in the input. All right. So going back to the Hyena hierarchy, what they do is the kernels, the way that they parameterize them is to have them as a CKConv modulated by an exponential decay, right? So you have this, which is going to be like the CKConv, then you have a window that is going to look like this, and this is what you have as the result. It's important to note that since we're doing convolution, this is the value of, this is going to be the point that is going to be multiplying the last value of the sequence, right? So when you do convolutions, you flip them, the kernel. So this is the real convolution definition, not the one that is normally used. So that's why, not to be, yeah, it's important to have that clear here. And so what we have is, if we do a comparison between transformers, CKConv, and Hyena, in terms of global context, all of them have the same property. They can model global context. In terms of input dependence or input awareness, transformers are very good at that. Continuous kernels, since they're non-input dependent, they cannot really do this well. But Hyena, they have this weighting or like this input gating recurrency, whatever. And so based on that, they are able to achieve this property as well. There are questions whether this is as powerful as transformers, but we're gonna delve into that also later. In terms of complexity, and this is where the convolutional models are much better, is the complexity of transformers is very high, it's quadratic, but of continuous kernels and Hyena is L log L, because you can do convolutions on the Fourier domain, and that's quite cheap. So in terms of results, these results are a little bit outdated, I must say. They're like from 1 year ago, and the field is going very fast. But at the time, Hyena was able to outperform other variations of sort of fast attention modules, such as RVQV, which is a very popular one, and also GPT models. But also what is very nice is that you can use Hyena for vision transformers, etc. I must say here that they didn't really, that still needs to be done, but they didn't really use the full power of Hyenas for vision, because here they were treating the inputs as sequence of patches. So they were not really relying on through the structure of the inputs. But Hyena is able to do that very easily because it's just a convolutional model. So I would expect this to go higher if you were to do it that way. Also, they use Hyena for very long sequences. So they treated DNA sequences with Hyena, and they were able to treat sequences that were up to 1 million tokens and work with them very well. So that's only to show the context that this kind of models can achieve, which is quite huge. And of course, doing this directly with a transformer would be very difficult. You would run very fast out of memory because it's just so expensive. All right. Before we continue, question: are Hyenas SSMs?
No.
No? Okay. Why?
Because they are convolutional.
Yeah, but SSMs are also convolutional.
Are they?
Yeah. So the answer is no. SSMs are models that are simultaneously, and that's the key, convolutional and recurrent. Hyenas are not recurrent, they're only convolutional, okay? And so this has an advantage and a disadvantage. The advantage is that Hyenas are able to describe a much more general family of convolutional models, right? But at the same time, because it does not have this recurrent mode, it cannot be changed into a recurrent mode during inference. And so the complexity of sampling is going to be OL instead of O1 for recurrent models. Right. So let's discuss the properties of this kind of convolutional, broad convolutional models before we go into the next topic. And there is an important thing here that we need to understand well before we go to Mambas, and is that SSMs and generalized convolutional models, they are linear time invariant. So what is a linear time invariant system? A linear time invariant system is a system that is linear and also time invariant. And time invariance in signal processing is the same as what we would call in deep learning literature time equivariance, where basically you say that if you apply a system an input to a system right now or t seconds in the future, the output would be the same up to that same translation. So it's just basically time equivariance. This is important because some data, actually a lot of discrete data, is not LTI. For instance, text, right? In text is not the same. The position of where the token comes is quite important. It's not only based on the relative positions, it's based on the position at all that it has within a sequence or a text or something like that. And so this is not, text is not LTI. The problem is that if you use convolutional models or SSMs, right, for problems that are non-LTI, then you're going to have an overly constrained model because you're using an LTI model to model things that are non-LTI. There is always going to be a gap between the family of functions that you want to approximate and the family of functions that you're actually using. So in order to do this, or in order to tackle this, Mamba actually gets rid of this LTI property of SSMs to be able to create a model that is able to describe non-LTI data like text much better. And that's what we're going to discuss now. So we talked about generalized convolutional models, right? Basically, we got rid of the convolutional part, of the recurrent part, to go into the convolutional direction. Here, we're going to talk more about generalized recurrent models, in which you get rid of the convolutional part to have recurrent models that are purely recurrent, but that have other properties. The motivation of the paper, of the Mamba paper, which is also called Selective Structure State Spaces Sequence Models, or X6, was this task that is called selective copying task. So basically, there is a task that has been used for a long time. Actually, it's not used that anymore. I would say that it's solved by now, but back in the days, of 4 years ago, there was a task that was called the copying task, in which you have a sequence, and what you need to do is, you need to copy the inputs that you saw at the beginning of the sequence back into the output, right? And the sequences are always going to be the same length. So this will be 100, 200, and you want to replicate the last 40 or last 50 tokens. And as you can imagine, because the distances are always the same, LTI models, like convolutional models, are able to solve this very easily, right? So you can imagine that if you have a convolutional kernel that has only one peak, right, at the very beginning, and the rest is 0, the output is going to be that peak. And so you're going to be able to solve this task very easily. The problem is, what if the tokens that you want to copy are now just randomly placed in the input sequence? If you only have this convolutional model, then these kernels, like the positions, cannot be stored in the weights anymore. And so you need to be able to selectively choose which of parts of the input you are going to get into the output, right? And what they show in the paper is that existing models like S4 or H3 or even Hyena, they were unable to solve this task. But the model that they propose, called Mamba, and also transformers, they're able to solve the task without no problem. I must say that I think that if you have a proper convolutional model, you still would be able to do this. The thing that you need to change is how you do the input dependency. Because in principle, if you are able to change the convolutional kernel based on what is in the input, you would be able to solve the task as well. That's an experiment that I still need to do, but I will do it at some point. Right, so in order to solve the task, what they propose in Mamba is to have a selection mechanism, right, that is gonna control how information goes into the state, into this XT, right? So basically what they do is that they make the parameters B, C, and delta functions of the input. So they go from this formulation here, the one that we had at the beginning, the SSM, and they transform it into this, where now the B, the C and the T and the delta, which is the parameter that you use for discretization, are going to be functions on the input. And so if we were to describe SSMs like S4 in terms of an algorithm, you would have that A, B, C, and delta, they are all just parameters, right? And then when you discretize, you're going to have this A bar and B bar, and you would do the SSM normally. So nothing is input dependent. What they do here is just they make B and C and delta input dependent. So now they are actually a linear function of the input. And based on that, you're going to have a hidden state, A and B, or like parameters of the SSM, sorry, A and B bar, which are dependent on the input. And by doing this, then you are going to have an input dependency in your model, right?
So here the linear is just literally just a linear matrix. So it's quote unquote matched across both B and the length in 6 length, right? Not just
exactly.
So
yeah.
there's not going to be a different value for different points in the sequence. It's going to be the same matrix for it.
Yes, exactly. Yeah. So probably there are also better ways to do the conditioning, right? That's I guess that's what you're trying to say.
I was just wondering because I'm thinking back, the time, the complexity of calculating things in transformers. Also transformers are using an NLP to also
a linear layer, right? They use a linear layer for the predictions as well.
Sorry.
Yeah.
Not even MF. They use just a simple linear map there, but then because they're computing a matrix after that, that's what is expensive. Right? And that's the square comes from there.
Yeah. So you don't have that here. So this is a little bit related to this other kinds of recurrent models that have like a gate, etc. You can think of these things now serving as a gate, because as you see, the B term is gonna tell you how the state changes. And so based on the value of B, your input is gonna be ignored or not, right? First, that's the first part. And the second part is that the C, you can think of C as, remember that when we were discussing the SSM formulation and Hippo, well, we had in the hidden state some sort of projection of the input in this n-dimensional space. And so this C now is going to be telling you how to modulate these functions that you have based on the input, such that you have some sort of input dependency, if that makes sense.
Yeah, it makes sense.
So based on this, actually, this is something interesting, I think. If you were to ignore this part, right, and we always only look at this, we could also have this in a convolutional neural network, right, where the C, you have some sort of basis functions, and based on the input, you could like remodulate how they're going to be used in the output. But the thing here is that this has a positive thing, right? Now we have an input-dependent system, but it also has a negative thing. This system is not an LTI system anymore. The reason for that is that if you take this formulation, you are not going to be able to transform it into a convolutional mode. Why? Because if we look at the convolutional mode, what you would do is you would multiply A a lot of time by itself, and then you have C and B. So you're going to be multiplying all of these things with one another. And these things are independent for each position. And that means that you can use the same everywhere. But now all of these things are depending on each position and where you are. And so you cannot really transform this into a convolution anymore. And these are a problem, right? Because if you remember, in SSMs, they use the convolutional mode to train fast, and then the recurrent mode to inference fast. But if you don't have the convolutional mode anymore, then you would need to train in a recurrent form, which is extremely expensive. That's not done anymore, right? You cannot use GPUs for that. So that's something that we need to solve. So if we go back to our diagram, right? We have SSMs in the middle. We have recurrent models here on one side. We have convolution models on the other side. We have Hyena here under the convolutional modes that are not SSMs. And we have Mamba here in the recurrent modes that are not SSMs. So as I mentioned, there is a problem here that we cannot use this convolutional mode to train anymore. But there is something still quite interesting that we can use to speed things up, which is based on parallel scans. And the authors not only use this, but they also have a hardware-aware implementation of these parallel scans to make this much faster. A little bit like flash attention did for transformers. So that's also quite a nice contribution. So what are parallel scans? Parallel scans is a technique that is used in computer science to compute cumulative sums and stuff like that very fast. So let's imagine that we have a problem in which we want to compute y. We have a vector, which is simply the cumulative sum of the input, right? So we have 3, 2, 3, 1, 2, 4, 0, 4, 1, 1, 3. What we would like to have as output is 3, 4, 6, 10, 6, 10, 11. So you're just summing whatever you had in the back. Now we do this in a recurrent manner, but a sequential manner. This would have complexity that is just as equal as long as the input, right? But if we use parallel scans, we can do this in log L time instead of L. The idea here is that you have two parts. You have a of the tree part in which you construct a tree, and then you start working locally. Like basically, just as in everything in computer science, you start dividing everything by 2, just trying to make things faster. And so you have the left and right values of each of the 2 things that you have here in the input. Then you compute the sum of you save the left in the register, and then you compute the sum, so the 4, right? And you do this up to the parent, up to the top. So here you have 3, so 3, 1, you save 3, you get 4 to the second node. Here you have 2, 0, you save 2, and then you give 2 further. Now here we have 4 and 2, we save 4, we give 6 to the top, and so on and so forth. Then we have the down the tree path in which we set the root to 0, and then we send the register to the left. You send the value from the top to the left, and then you set the value from the top plus the register to the right. So here we had 0, 6, here we have 0, that's 4, then here we have 4, here we have 0, and then 3, and here we have 4, right? And then 2, that goes here, right? And by doing this, then you get these values here, and abracadabra, when you sum them up with x, you get what you had before. And if we look into the formulation of Mamba, we have a recurrency here, right? Which is linear. And because it is linear, it means that we are going to be doing sums and multiplications. So there is also a formulation in which we can sort of do Mamba in a way that resembles this. And the idea here is that you have this recurrence, right? HT equals AHT minus 1 plus BXT, right? And you define a new sort of associative operation. You say you have these tuples, and with these tuples, you're going to do the operation that is shown here. And so you construct a tree going up as is shown here. And if we look at the terms here, already by going up, we already have H1, we have H2, and we have H4. Now, there is also an associative operation for the down pass. And so when you go up and down, you're going to have all of the things for the whole sequence. This is basically the key of how they solve the problem of not training recurrently. Now, it is important to show to highlight here that if this was a recurrency that was nonlinear, you would not be able to do this. So this linear recurrence is still quite important here. And so by doing this, they're able to train Mamba very fast, like 5 times higher, much faster than what you would need with transformers. And it has still 5 times higher throughput than transformers because they have like this recurrent form, etc., etc. Clear?
Yeah.
Great. So that's actually it. So they took the SSM, and they also, well, in top of the Mamba way of mixing that they provided, they have this, they propose this homogeneous backbone for SSM models, which actually combines a lot of developments in LLM literature, like the Swiglu group and everything, Swiglu nonlinearity. And so what they have is, here's your input. You upsample it by 2, or you upscale, not upsample, you go to how do you say, you upscale the hidden dimension by 2, and then you do a small convolution. Honestly, I still don't understand why they need to do this convolution still. So they have this convolution here at the beginning, which is a very short one, 3 by 3 or 4 by 4. Sorry, only 4. And then they deploy Mamba, and then you just use some sort of gating with the input. Right? It's important to know that this is only the mixing operation. That means that there is still a recurrent branch going here like this. A residual branch, sorry. Right. Also something that is quite interesting, I forgot to mention that before, but I'm gonna say it now. If you look here, they modify the B, they modify the C. You don't need to modify D because this is only some sort of a residual connection, right? So you're just putting U into the output as well. But if you notice, the A, they are not touching the A. And if you remember, we were talking a lot about Hippo and how Hippo was important, saving memory, saving everything to memory and so on. This is only to showcase how important this matrix is, right? So I think they also had experiments, but that didn't work out that well. If you mess too much around with this matrix, then you have something that does not work as well. Now, I remember also there was a question about the structure of A, right? And at some point, you have this matrix that is diagonal plus a low part that is normal. And then there was this new development that said, hey, just put this part to 0 and you just use the diagonal. In Mamba, they use the diagonal. Basically, because here you're still doing a lot of multiplications of A by itself, or like versions of A. And so if you have different versions of A with a lot of structure, like let's imagine that all of this is a full matrix, this is still would be so expensive to calculate. But if you structure all of this to be diagonal, then you can do this very fast. This is just multiplying the diagonals of everything. And so this is really, really fast. So that's also very important here. So let's look at some results. Mamba has incredibly good results in a lot of different tasks. So they were able to surpass transformers actually in different tasks that they show in the paper, and also other variations of linear transformers like RV, KV, and some others, also hybrids with H3, yeah, a lot of different models, and they were actually quite well. They work quite well. If you look at the scaling laws on the pile, you see also that Mamba is lower than the Transformer++, which is like the modified best version that there is of Transformers. So this is really, really awesome. On sequences, on DNA sequences, they also did the same. And basically you see Hyena going here and Transformer going here, but Mamba is also lower. And in terms of perplexity, yeah, Hyena is also better than, sorry, Mamba is also better than Hyena for this kind of DNA sequences. And if you think about it, it makes sense because as we were mentioning, text and DNA sequences, they are not translation equivariant, right? They are very well structured, they're discrete, etc., etc. So it makes a lot of sense that this is the case. On the other hand, they also had experiments with audio. And what you see in audio is that Mamba performs very poorly even in comparison with S4, which is non-input dependent. And so here, you see the Mamba here on the top, and you see the bits per byte. And here you see all of the other versions, right? Like S4, etc. They don't even compare with Hyena here. I think Hyena would be even better because Hyena has this input dependency. So this is to show that it's important also to think about what kind of data it is that you are handling. So those are the good things, but there are also bad things about Mamba, and people have started to think about this a lot. So, like in Mambas, like in SSMs, you have this latent space, right, which has fixed dimensionality. And so you have a recurrent network that is basically doing compression the whole time. And so there was a paper that was evaluating how good was Mamba in copying things from the input to the output. And so if you go over the n dimension that you have, basically everything starts to break down. And even though they have this recurrent or like this gate that allows you to handle the state, how the state preserves memory, this is still an issue that I would say, and I think that's the conclusion of these studies, all models that are recurrent would have, because they are still doing compression anyways. So there's some sort of inherent thing there that you cannot get rid of. So yeah, so I'm going to talk about. So in conclusion, Mamba is a model that is really crazy how good it works. It works very well. I also have used it myself, and it's really nice. And it is very nice for non-LTI data, such as discrete data. But because natural data like images, audio, etc., are still LTI, right? It is likely that LTI models are going to work best, right? Makes sense. And the other thing is that if you look at the problems that we were talking about in terms of like saving, etc., or compressing in the recurrent state, etc., the models that are probably going to work the best for non-LTI data are hybrids, likely with transformers, not with convolutions. I would think so. I would say that this kind of hybrid models would be the ones that have the best performance, because they would have a little bit of fast inference, but they would also have the ability of transformers to still, like have access to the whole sequence. And so the question here is, how do we hybridize models? And there are already some models such as Jamba that combines Mamba and transformers. And basically they use a Jamba block, which is 7 Mamba blocks and 1 transformer block. And that works better than Mamba and is faster than transformers, etc.
That's the first approximation, right? You just stack both of them together, see what happens.
Yeah, and there is another one called Samba, which does something similar but in a different way. Like they have the transformer layers on one side, and then they like sort of gate. And yeah, I haven't looked into that architecture that much. Yeah, questions about this part?
So you think you're saying you think any combination of Mamba and transformers will work
best? Yeah.
Not convolutions. Is it because
for non-LTI data? Yeah. Yeah. Because it adapts very well, and you can see that also here, right? It adapts very well to the non-LTI data setting, but in LTI data settings like audio, etc., convolutions are much better still. And the question here is, we need to find a way to do convolutions in an input-dependent manner that is stronger, that is very good, such that we're able to do that properly. Yeah. And why do I think that the hybrid part is important? Is because recurrent models have the limitation of having a very limited hidden space in terms of like the recurrent state. And so if you want to like alleviate that thing, you should combine it with something that doesn't have that problem, but that is that is in a model that is still fast. More questions? No? All right. So let's take a look at the conclusion. In conclusion, we have seen different models, right? We talk about SSMs, we talk a little bit about transformers, we talk about generalized convolutional models, and we talk about generalized recurrent models. There are all these different models, and they have, of course, different properties, and you should be aware of which properties they have. So if you're going to remember anything from this talk, please remember this slide. So let's go one by one through all of these different things that these models have. So in terms of global context, generalized convolutional models and transformers have them 100%, right? Whereas SSMs and generalized recurrent models have also global context, but they have certain limitations here related to the size of the latent space, right? So you would say that they have global context, but you should be aware of this. In terms of input dependence, the recurrent models seem to be very good at this, and transformer models also are very good at this. SSMs do not have this property at all, but generalized convolutional current models can have this, like in Hyena, right? I'm putting this also with an asterisk here because it is not clear whether Hyena is the optimal solution. I think there are much better solutions to the problem. And so, yeah, it's important to be aware that there is still something to happen. Something needs to happen in this direction to make this better. So there is a future, I would say, for more powerful generalized convolutional models. In terms of training complexity, we have the generalized convolutional models and the SSMs. They have L log L. So those are the fastest. We have transformers, which are quadratic, and we have generalized recurrent models, which are higher than L log N, but they're still linear. So they are lower than this, right? And the reason this is not L log L and it's there with an asterisk is that in principle, when you do the parallel scans, you would also have log L complexity, but because they have this associative operation that is doing multiplications with itself, it's going to be higher than that, right? In terms of autoregressive inference, the convolutional models would have complexity OL, right? Because they need to save the whole path to be able to do the next prediction, just as transformers do. Whereas SSMs and recurrent generalized models, they have constant memory complexity. In terms of having a fixed state size, SSMs and generalized recurrent models have a fixed state size due to their recurrent nature, but transformers and convolutional models do not have that. In terms of LTI, SSMs have the property. Generalized recurrent models and transformers do not have that property, right? You need like fixes in terms of like adding, how you say that? Like positional embeddings, etc., but they're inherently not LTI or translation equivariant. Whereas convolutional models are. I'm also putting the star here because if you were to, if you find a way to do add input dependency to convolutional models in a good way, you would have it, but you will still have the input dependency, right? That's why there is a star or like an asterisk there. In terms of multi-dimensional support, the convolutional models are the only models that have this. All the other models do not have this inherently, but you can do modifications such that they have it a little bit, like by adding positional encodings or by using multiple SSMs going by directions, going multiple dimensions, etc. But it's still going to be, it's still not going to be better than convolutional models in that sense. And in terms of being bidirectional, it also is the same. So convolutional models are bidirectional. Transformer models also can be bidirectional. And these RNNs and SSMs are not really inherently bidirectional, but you can make them bidirectional by like having two that go like this, but it's still not going to be as powerful. So in summary, for discrete non-LTA data, generalized recurrent models in combinations with transformers are likely to work the best. For natural data, images, videos, audio, generalized convolutional models are likely to work best, probably also in combinations with some kind of other models, maybe with transformers as well. Once you have tokenized the inputs, you could have some layers there, a little bit like Mamba, Jamba was doing that for Mamba. And there is also an important part, and is that with diffusion models growing up in interest, there is a question of whether autoregressive inference is going to be important in the future. And so in the future, if you don't need to do autoregressive inference, well, this O1 of RNNs is going to disappear. It's not going to be important anymore. So I would say that it's also something to keep in mind going forward. Right. With that, I would like to finish my presentation. And also, if you're interested in this kind of research, we at NVIDIA are hiring actively to work on these kind of problems. And if there are any questions left, please let me know.
Thank you. Nice.
Sadly, there are no students here.
Okay,
I don't think I have any questions left.
Okay.
No, I guess it's mostly just a high-level question of what do you think? Like, obviously, we're seeing this input dependence is super important. This ability to be more linear and less quadratic in terms of complexity also seems attractive.
Mm-hmm.
And it seems also to kind of scale in terms of the performance, as we saw with the graphs. Then we also saw that however this like forcing a state that memorizes the past would definitely always have problems in some tasks.
Yeah.
I guess the overarching question is: do you think this is there are some trends that you see that are important in terms of the type of architectures that we will see in the future, or is there always a success of transformer, or is the success of transformers just a product of the super success of ChatGPT like autoregressive models? Like, what is your opinion in terms of the type of architectures, the type of tasks that we will see as important in the future?
Yeah. Yeah, so I think that hybrid architectures are definitely going to be something important. So transformers, if you look at how transformers have been made to work on natural data, is with patchification, right? If you don't have patchification, basically they don't really work well. So that shows that there is an inherent limitation there, right? So what I would expect is that going forward, tasks that are inherently LTI are going to need models that are LTI. But the reason that has not happened yet is because there is yet still no good way to do this input dependency with these convolutional models, right? So I would expect that having a very powerful convolutional model that is input dependent will solve these kind of tasks, and also would help a lot of the consistency problems that normally generative models have nowadays. The reason I believe that this is partly due to the fact that you're using a model that does not obey the laws that your data is trying to represent. And so if you're going to generate data from such a model, makes sense that the models that you're going to generate, the data that you're going to generate is not going to obey to this, right? So that's for the LTI part. For the non-LTI part, I would think that what would be very interesting in looking at is some sort of variation of Mamba, in which you don't have a recurrency anymore, but in which you have some sort of system that is non-LTI, and you could achieve that maybe with this kind of associative, with parallel scans kind of thing. So you could think about this as having some sort of Mamba that goes bidirectional, right? But that does not need to have like this condition to be bidirectional, but inherently is, right? So it's not a recurrent mode going in both ways. It's some sort of, it's just some sort of mapping that is looking at the whole thing as a whole. And combinations of this kind of data with transformers, I think that would work very well for text and stuff like that. So yeah.
Kind of like maybe the autoregressive is not necessarily what we want to.
About the autoregressive part, I think that the autoregressive models are gonna die out.
Why?
Because, like, I mean, like for us, it makes a lot of sense to have autoregressive models because that's how we generate text. But if we think about it, like when you're generating text, you already have some sort of image of what you want to write. And that's not really clear. I mean, of course, autoregressive models have this a little bit as well. But I would say that if, like you're able to diffuse the whole thing or look at the whole sequence and see what you have, and then you start like distilling it to go to the distribution of the data, that will work better. So I think that this kind of techniques that do discrete diffusion are very promising for like text generation and so on and so forth. And for natural data, I mean, like that's what they're using already have been using already for a long time. So I'm skeptical about how long we're going to keep using autoregressive models. They have a lot of properties that are very nice, like it's super tractable, etc. But as the field goes forward, I would say that might die out.
Yeah. I never thought about it, but I think like practical applications, I agree. Because in practical applications, theoretically you like to have this property that like it's only causal, let's say, right? It's only based in the past, but for a lot of things, it's not necessarily true that you want that.
Yeah.
You would like to process the whole answer, maybe not like completely at once, but at least be able to look at the future and then fix the past. It's not something that is impossible to think about.
Yeah.
It is a viable option.
Yeah. And if you look at how ChatGPT works, for instance, there is something problematic going on with ChatGPT, and is that the controlling part is difficult, right? So if you have something in the middle that you want to change, and there is a part in the end that you want to keep the same, if you do everything completely autoregressive, you don't have that control. It is very likely that that part is going to change as well. And so you need to be, like if you have like a diffusion-like thing that looks at everything and then progressively modifies whatever you want to modify, you're going to have higher control.
Yeah. And it makes a lot of sense. I mean, it's using the whole sequence during, I might be wrong, but it uses the whole sequence during training anyway. So
yeah,
the fact that it could use it also during inference. I mean,
yeah,
it's not being generated yet. Okay, just generate an initial.
The current solution for that is that, like you put first everything into like memory and then you generate from that. But it's still like, again, if you have tried this with ChatGPT, most of the times it changes things as well.
Yeah. So that's really nice. Yeah, I never thought about it. So I think that's a really nice take, actually. Yeah. Thank you.
Really all right. Thank you for listening. Thank you all also in the virtual audience, the people that were there following the tutorials. Yeah. Thank you.
Thank you.